The other question about probabilistic arguments, whether completely random or semi-random or any, is that it's very powerful to prove the existence of objects or with certain properties, but it doesn't tell you where they are. So you just don't. It's not completely satisfactory, in that often you would like to know where is the object you are looking for. If you don't have randomness, if you let's say construct a good Ramsey graph, construct a two-coloring which does not have large monochromatic subsets. So the probabilistic method, I mean, at least I personally don't find it completely satisfactory, and there are many problems for which getting a deterministic solution of a similar quality will be extremely important. So in particular, proving that certain problems are hard. We know that random problems are difficult. This is an application of the probabilistic method, usually, and we don't know how to exhibit hard problems. So the question is, maybe some intuition you have. I know you thought about some of these problems. Why is constructing such objects difficult when we know that almost all of them are of the type we like?
Let's go back to the Ramsey number and co-authors. Ramsey number, then Erdős' proof was probabilistic, but nobody could give a concrete two-coloring of the graph, so that there was no, I guess at the very beginning, square root and monochromatic square root, and definitely if we wanted a bipartite monochromatic square root and was for a very long time the best, and then the theoretical computer scientists came up and completely defeated the combinatories, because now I guess your best bound is not log n, yes, the best possible, but very close to it, yes? It's log n to the, what is the bound?
It's 2 to the square root of log n or something like that. Yes, so it's not a polylog, but it's much less than...
Poor combinatories never would have come even close to these things. So it actually required, also it was the proof, of course, contained a lot of combinatorial...
in particular, this Burgen-Katz-Tower result on some product.
Right, yes. But nevertheless, it needed, if we might formulate it, that a way of thinking how the theoretical computer science things, even when they think about combinatorics, I believe then they look at it a little bit differently than, for instance, I would look at it.
Maybe we are more liberal in that we allow ourselves any algorithm to generate the object we want, as opposed to just asking for it to be a polynomial, which is a more mathematical thing. But still, so of course there are examples where there are explicit constructions of objects. Expanders are another beautiful example. But the most interesting problem to me is P versus NP, or more generally proving that some natural problems are difficult. And we cannot do a single example of this, even when we are limiting what we call hard to something which is almost completely trivial. The usual way to phrase these questions is about constructing an object. You can ask any mathematicians, any high school student almost, to find a matrix. So not only does it have high rank, but also if you change just a few of the entries, 1/1,000,000 of the entries, it remains high rank. A random matrix has this property. This is true over any field you want. And I guess you can answer, you don't know why this should be hard, but it seems that combinatorics solve much harder problems.
Seems, but may not be the truth, because maybe then this is really, for some reason, it's a very, very deep problem. So there must be some reason then so many strong theoretical computer scientists and even mathematicians have been working on it. For me, this is a good enough explanation. Then so much energy has been devoted to solve this problem. It's a beautiful problem. It's one of my favorite problems. I tried without absolutely any success, well, you had and your group some success, but yes, the problem is still open. No, this is very, very hard, and I am not sure that this is combinatorial by nature. Actually, once we are here, you were the one who told me this problem, and this is my plan, but maybe by the time I will...
That's one of the problems you didn't mention that you are going to work on.
Yeah, right.
Okay, now it's out. Yeah.
Okay. So you should be, how do you call the ones who are searching for the secret of others? That is one of the problems. The another one is almost not the same, but in some sense close. You know this problem, and this is really shame. And then if we have a circuit which the depth is log n and the size is linear, that give a concrete Boolean function which cannot be computed with such an animal. Yeah. That is one of my favorite, and that is actually our common shape, both for the combinatorial community and the theoretical computer science community. Even the first step. Yeah. This is like inhalable problem for the 4 points. Even the first step is not done in that direction. But it's a beautiful, beautiful problem, and who knows in 5 years, because now a lot of other methods came into the place, so maybe.
This is one of the results with you had with ITAI and Komlos.
Yes.